talk a little bit about the sandwich theorem, also known as the squeeze theorem. So what this looks like, if you have a function, say f of x, and it's in between two other functions, so g of x is below f of x for all values of x not equal to a particular value we're going to look at, and f of x, this function, is below h of x. So basically f of x is sandwiched in between g of x and h of x, or it's squeezed in between. So that's where these names come from. And if you know something about the limit, so if you know the limit as x approaches some value c that's in an interval within that function, defined in that function. So if the limit as x approaches c of g of x equals the limit as x approaches c of h of x. So if the limit of the function on the left equals the limit as x approaches a particular value of the function on the right, then that limit of f of x, the one that's in the middle, as x approaches that same value, has to be equal to that same thing. So this is kind of how it works and how we would prove this. Now, for example, if you were just to plug in x as 0, because that's how we try and figure out the limit first, is plug in a 0. Obviously, we have a problem because you can't take 1 divided by 0. So we have an issue there. So we can't really do something algebraically. Now we can look at a graph, we can kind of approximate what we think it is from a graph or a table, but I want to show you how to do this with the sandwich theorem. So what I'm going to start with is the idea that sine x, or sine 1 over x, is always in between 1 and negative 1. Okay, remember, if you think about y equals sine x, the graph, remember that the highest it ever is 1, the lowest it ever is negative 1. It looks something like this. So we know that sine of anything has to be in between negative 1 and 1. So what I'm going to do next is I'm going to multiply each part of my inequality by x squared. Now, I know I can do that without changing the inequality symbols because x squared is positive. Even if x is negative, if I square it, it's positive. So if I multiply each piece by a positive value, then my inequality symbols won't change. So this would also have to hold true. So then, according to the sandwich theorem, we know that the limit as x approaches 0 of negative x squared has to be less than or equal to the limit as x approaches 0 of x squared sine 1 over x has to be less than or equal to the limit as x approaches 0 of x squared. I shouldn't say I've used the I haven't used the sandwich theorem yet. I'm getting ready to. This is just going to hold true for the limits. It would have to be true as well. So I'm kind of building the statement. Now I've got this situation up here because I know that my function in the center has to be between these other two functions. Well, we now know something. We know what this graph looks like. Y equals negative x squared. We just have a parabola opening down. But we know that we can just plug in a 0 here. So the limit as x approaches 0 of negative x squared is just 0. Recopy this. And we know that the limit, this is just the parabola opening up, and we can plug in a 0. So we know that answer is 0. So now I'm going to make use of the sandwich theorem or squeeze theorem, which says that means that the limit as x approaches 0 of x squared times sine 1 over x has to equal 0. That's how I use the sandwich theorem. Here's a graph of that same situation. So in blue, you see y equals x squared. In green, you see y equals negative x squared. And here is that the other function, x squared times sine 1 over x. And notice how the function is sandwiched between those other two functions. So you can kind of see graphically how the answer would be 0, but also how it's sandwiched between or squeezed between. And that is the squeeze theorem. There's some other examples on AP Classroom on a video that I'm going to have you watch so that will give you another example of that.